All right, relative rates of growth. So here we go. I'm going to put some definitions first. If f of x and g of x are positive. Now, when I say positive, I mean for x's that are sufficiently large. So at some point, they both become positive and then positive forever after that, okay? So let's just write that down. For x values that are sufficiently large, now, what we're going to be talking about is who gets bigger faster. So, relative rates of growth. Does one function grow more quickly than another? And you hear, somehow or another the media has picked up on exponential growth. You started hearing that a lot in the media in the last few years, especially when it comes to or rates of inflation, which I think we talked about last time, right? And what happens to money and how it devalues at an exponential rate as inflation grows more quickly. So a question would be then, well, what about exponential functions and polynomials? Is there some relationship in their growth rates? That kind of thing, or log functions. What about log functions? How quickly do they grow relative to polynomials or exponential functions? That kind of thing. Okay, so here's what we're going to say. We're going to say that f grows faster than g as x goes off to infinity if the limit as x goes to infinity of f of x over g of x is equal to infinity. Now that is the same as saying that the limit as x goes to infinity of g of x over f of x is equal to 0. If they're both positive, those two statements are really equivalent. Okay, so f grows faster than g, or you could also say that g grows slower than f. It's the same concept. Okay, now, so this would be the first thing we're going to write here. The second thing we're going to write here is, well, here we've got one of them growing faster than the other, but maybe it's possible that we have two functions that are different, but grow at the same rate. Okay, so f and g grow at the same rate as x goes off to infinity if the limit as x goes to infinity of f over g is equal to some limiting factor that is some finite positive value. So if that limit is constant, then they grow at the same rate. Okay, so what might be some examples of this sort of thing? Well, let's see. Okay. So let's look at specifically f of x equal to e to the x and g of x equal to x squared. Okay, so we've got an exponential function and a polynomial. So what happens here? So what we're going to do is we're going to, let's go back over here. It looks to me like I need to look at the limit as x goes to infinity of the quotient of those functions, okay? So the limit as x goes to infinity of f of x over g of x. Okay, so that's going to be the limit as x goes to infinity of e to the x over x squared. But the problem here is this is what would you get if you put infinity in for x? Which is not undefined. Indeterminate. It's indeterminate. Now, if I have an indeterminate limit, then what can I do? L'Hopital's rule. Very good. Very good. Very good. So we're going to do L'Hopital's rule here, and you always want to indicate that these limits are equal, but that you're applying a theorem. So we have the limit as x goes to infinity. Okay, now remember that it's not the quotient rule, and that's a mistake that people often make. It's the derivative of the top and the derivative of the bottom individually. Okay, so the derivative of e to the x is just e to the x. Derivative of x squared is 2x. Still indeterminate. But L'Hopital's rule doesn't say you can only do this once. It says any time that we have an indeterminate limit, infinite limit, then we can apply the rule. So here we go. This will be e to the x over 2, which is infinity. So what did we just find? Well, according to this definition back here, it says that if that limit is infinite, then f grows faster than g. So what we just found is that e to the x grows faster than x squared as x goes off to infinity. Okay, any questions about that? All right, so let's look at, what about f of x equal to 3 to the x and g of x equal to 2 to the x. I mean, it looks to me like 3 to the x is bigger than 2 to the x. But we're not talking about like how big they look. We're talking about how fast do they grow, right? That's what we're thinking about here. All right, so let's see. I think we still need to do this limit as x goes to infinity of f of x over g of x. All right, so let's see. That's going to be the limit as x goes off to infinity of 3 to the x over 2 to the x. Now, I got to figure out what to do with this here. Clearly, it's infinity over infinity. But what about the derivative when the variable's in the exponent? Well, I'm not quite sure I need to worry about that. Can you think of something else you could do with that? What about your exponent rules?
Subtract the exponents.
If we had the same base. And our bases aren't the same, but we're thinking along those lines, though. Think about your exponent rules. What is an exponent rule that you could apply here?
You can pull the x out.
Yeah, remember that a quotient raised to a power, you put the power on each the top and the bottom, right? Oh, I think we know what that is, don't we? If you take something bigger than 1 and raise it to bigger and bigger and bigger powers, what happens? Multiply it by itself over and over and over and over. If it's bigger than 1, what's happening? Yeah, it's going off to infinity, isn't it? What if I'd have put the 2 on the top? What if I'd have had 2 to the x over 3 to the x? I would have had a number less than 1 that I kept multiplying by itself. What happens when I do that? Yeah, it goes to 0, doesn't it? So I get the same result either way. Okay, good. So we would say then that 3 to the x grows faster than 2 to the x. which seemed about right. It ought to. Yes, sir.
Is this only when x is approaching infinity that it grows faster? Or is it...
That's what we're thinking about, is x goes to infinity. And this is foreshadowing, because after a while, not like right away, but pretty soon, we're gonna hit some material where that's what we're gonna be thinking about, is lots and lots and lots of infinity and lots of terms. Yeah. Okay. I know what you're worried about. You're worried about log functions. Okay, so let's look at f of x equal to x squared and g of x equal to the natural log of x. Okay, so well, with the exponential function, it grew faster, didn't it? What about the log function? Well, just find out. So we'll do the limit as x goes to infinity of x squared over the natural log of x. I'm in the same situation, right? I've got an indeterminate form. Okay, so I can use L'Hopital's rule, and that would tell me that the limit as x goes to infinity would be the same as 2x over 1 over x. Now I need to do a little bit of algebra here. So this is going to be the limit as x goes to infinity of 2x squared, right? That is definitely infinite. So we know that 2 to the x grows
x squared? Or is it...
faster. X squared grows faster than the natural log of x. I bet you 2 to the x does too. Okay, good. Any questions about any of this? Okay, so I would like for you to think about f of x equal to the natural log of x and g of x equal to x to the 1 over n. That's interesting. Now, what's getting bigger, n or x? Yeah, and so n is fixed in this case, right? N is a constant in this situation. We're not doing the limit as n goes to infinity, or limit as x goes to infinity. So we can treat n as a constant with regard to the limit. Now, we start out with an indeterminate form again, right? They're both going to be infinite. Okay, so let's see. So let's see, I'd have the limit as x goes to infinity of 1 over x over, now, I bring the 1 over n down times x. Now, I subtract 1 from 1 over n, right? So I have 1 over n minus 1, like this. Okay, but now I'm subtracting exponents. And so I think about that. And when do I subtract exponents? When I do what? Yeah, divide with like bases, right? When I divide with like bases. Okay, so that would be the same as the limit as x goes to infinity of 1 over x over 1 over n times x to the 1 over n over x, right? because that would be x to the 1 over n over x to the 1, and I would subtract exponents. So those would be equivalent. Now, so then what is this the same as? So this would be the same as the limit as x goes to infinity of, now, let's see, I'm going to invert and multiply, right? So I've got 1 over x on the top. And on the bottom, I've got x to the 1 over nx, right? Okay, so that means that nx goes on the top, and x to the 1 over n goes on the bottom. And the nice thing is that those x's are going to cancel. So we've got the limit as x goes to infinity. Now, I've got n over x to the 1 over n. What's that going to be equal to? It's messing with us. What's that going to be equal to?
0.
Yeah, that's 0, isn't it? That's a constant over a number that is increasing without bound. So that's going to be equal to 0. So what do we know?
Natural log of x grows slower.
Yeah, very good. So because that was 0, natural log of x grows slower than x to the 1 over n. Because that was one of our little definitions here. That these things were equivalent. This and this. Okay, any questions?
So for any value of n, the natural log x will always grow slower.
If yeah, n has to be constant, right? And it is because with regard to our limit, the only thing that's varying is x. N is not varying with regard to the limit. And could vary in some circumstance if we define it as something that's varying. Okay, and that will become a thing, by the way. That'll become a big thing.
For sure.
Okay, let's see. There's one specific one that I want to look at here. Oh, yeah, here, let's look at this. So let's find the limit as x goes to infinity of a to the x. Oh, no, I'm sorry. Of log base a of x over log base b of x. And let's say that a and b are both greater than 1. They have to be, don't they? Because in order to take a log, your base has to be something bigger than 1. It has to be positive. So a and b are bigger than 1. Okay. Wonder what happens here. Well, I mean, I'm going to have a hard time doing very much algebra on this thing when I have different bases, aren't I? So I'm thinking it'd be kind of nice if I could change the same base. Okay, so I could do that. This would be the same as the limit as x goes to infinity. And we'll just use natural log because, you know, we got so many formulas there. So that'd be the natural log of x over the natural log of a over the natural log of x over the natural log of b. Okay, so now let's see. That'd be the limit as x goes to infinity. I would invert and multiply again. Natural log of x over natural log of a times natural log of b over the natural log of x, but those cancel. And we wind up with, well, the x's are gone. So it's really the limit of a constant, isn't it? What's the limit of a constant?
They grow the same.
It's just the constant, isn't it? It's the constant value. There's no x to plug in there. It's like this. What's the limit as x goes to infinity of 2? When x is infinity, what's 2? Yeah, it's still 2, isn't it? Yeah. So this is just natural log b over natural log a. Now, if a and b are bigger than 1, and that's a constant, then what did we find out?
They grow at the same rate.
They grow at the same rate. Very good. So in other words, these log functions are going to grow at the same rate, no matter what the base is. Okay? So log base a of x and log base b of x grow at the same rate. That's kind of fun, isn't it? Yes, sir.
And that's also true for the log base e, which is the natural log, correct?
Well, you know what's funny is that I had a professor in graduate school that would say, well, there's only one log. So it doesn't matter what the base is. Log is a log. Yes, so that's true. That would be right. Okay, so I know what you're wondering. You're wondering about the square root of x squared plus 5 and 2 times the square root of x minus 1 squared. I have absolutely no idea in the world how to compare those two. But I do know how to compare each of them to something else. Like, for instance, I know pretty well what y equals x does. What we're going to do right now is go through the process of determining which one grows faster if one of them does. Okay. And let's do that by comparing them both to y equals x. Okay, so let's do the limit as x goes to infinity of the square root of x squared plus 5 over x. Let's start that way. Now, I'm thinking about this. I could write that as the square root of x squared plus 5 over the square root of x squared. I could do that. And why would I do that? Well, because when I have a square root on top and a square root on bottom, I can make it all one big square root, right? So this would be the limit as x goes to infinity of big square root x squared plus 5 over x squared. And that I could write as the limit as x goes to infinity of the square root of x squared over x squared plus 5 over x squared. And that would be the same as the limit as x goes to infinity of the square root of 1 plus 5 over x squared. Well, as x goes to infinity, 5 over x squared is going to 0, right? And that just leaves me with the square root of 1, or just 1. So that tells me that the square root of x squared plus 5 and x grow at the same rate. Okay, then what about the other one here? What about the limit as x goes to infinity of 2 square root x minus 1 squared over x? Wonder if I could do something similar. So let's see. It'd be nice if I could get them both under a square, right? And I could if I wrote that as the square root of x squared. Now I have the same exponent on the top and the bottom. So I can write it under 1 exponent of 2. So I have the limit as x goes to infinity of 2 root x minus 1 over the square root of x squared. And now I can do something similar, right? I can make 2 fractions out of that. So I'll have the limit as x goes to infinity, 2 square root of x over square root of x minus 1 over the square root of x squared, which would be the limit as x goes to infinity of 2 minus 1 over the square root of x squared. Square root of x, as x goes to infinity, is still going to infinity, right? So I have 2 minus 0, or 2 squared, or 4. Okay, now here's what I want to think about. One of them had a constant of 1, and the other one had a constant of 4. What does that tell me?
Do they all grow at the same rate?
Why? They're different.
The constant was just to verify that they grow at the same rate. But
Ec-
it didn't have any significance to the actual said rate.
Very good. So, go through the logic. So here's the logic. The logic is that the square root of x plus x squared plus 5 and x grow at the same rate. Well, that last result it's just constant. Doesn't mean anything about who's bigger. It just says how fast they grow, right? And what we found is that 2 times the square root of x minus 1 squared and x grow at the same rate. So I believe we can apply the transitive property here, right? So therefore, square root of x squared plus 5 and 2 root x minus 1 square grow at the same rate. We're not talking about how big they are, we're talking about how fast they grow. Okay? Now, there's some notation I do believe that your book is going to utilize. A function f is of smaller order than g as x goes to, oh, I'm sorry. Oh, yes, this is what we want to say. As x goes to infinity, if the limit as x goes to infinity of f of x over g of x is equal to 0. Now, this is indicated, so we indicate this by writing f equals, now this is going to be a little o of g. F is little o of g is exactly how you say that. F is little o of g. And so it means that f is of smaller order than g if you have a little o there. Okay? Now, then we have a big O also. And that would be, let's look at a specific example here. Let's do that. So let's look at x plus sine x and x. So let's think about x plus sine x and x. Now, that's a little tough, right? Because what's sine x doing?
It's going back.
It's oscillating, isn't it? So it's adding some and then subtracting some and then adding some and then subtracting some. So let's think about the quotient. X plus sine x over x. Well, what's the biggest that sine x can be?
Pi. One.
The biggest it can be is 1, right? Now, so what I'd have is x over x, and if x is getting big at positive numbers, going to infinity, well, the x over x is going to be 1, right? No matter what x is. Then I'm going to either add a little bit or I'm going to subtract a little bit. But here's the thing. I know that is never going to exceed 2, right? That is never going to. So what I've done is I've found a constant. I've found a constant that I know that thing never goes past. It's like a boundary. We found a boundary for that value. So here we go. This is how we're going to define this. Let f of x and g of x be positive for x sufficiently large. Then f is of at most the order of g as x goes to infinity if there is a positive integer m for which f of x over g of x is less than or equal to m. So, at most, the order of g. At most, the order of g. Okay, so let's see. I found an m value, didn't I? 2. So that says that x plus sine x is at most the order of x. And we would indicate that with a big O. So we would say x plus sine x is equal to big O of x. It is of at most the order of g, because we found a bounding value for the two functions, for the quotient of the functions. So what are the two O's we've got? We've got a little o, smaller order, and we've got a big O, at most the order of g. So those are some questions that are going to come up, and you just got to look at. That's what you got to do. I mean, you just look at the quotient. You find the limit if it's 0, and then you look at the quotient, and if you can find the limiting value, then you have the big O. Okay? There's not much more to it than that. Let's suppose that we have the integral of 4 minus 32x over the square root of 9 minus 16x squared dx. Okay, so I'm looking at that and I'm going, The derivative of 16x squared is 32x. That's what you guys are seeing, aren't you? But you're also looking at that 4, aren't you? Darn that 4. Okay, well, maybe what I can do is turn this into 2 integrals. That would help, because the other one I'm seeing pretty clearly, right? So let's try that. So I'd have integral 4 over square root 9 minus 16x squared dx minus integral 32x over square root 9 minus 16x squared dx. Now let's deal with that first one first. So we'll go integral 4 over square root 9 minus 16x squared dx. We'll worry about that. Blast. You know, if that was in another form, like if it was in, say, the form of the square root of 1 minus u squared, I think we have a formula for that, don't we? That'd be arcsine, wouldn't it? Do you guys remember that from Calc 1? Examples of that? If I could put it in the form 1 minus u squared. So I kind of have to imagine, well, so let's think about this. Let's just goof around with some values of u. And that's what you're going to do. I'm not going to goof around with it because I know what it should be. I'm just going to say, let's let u, and then you're going to see why, okay? And you may already recognize it. But if I let u be 4x over 3, okay, then let's think about this. Then 3u, this would imply that 3u would be equal to 4x. And man, that's looking pretty good right there, isn't it? Because if I was to square both sides, I'd have 9u squared equal to 16x squared. Okay, now let's come back over here and say, okay, well, du then would be 4/3 dx, and 3 du would be 4 dx. Okay, so now let's do this. Let's make all those substitutions. What we're going to wind up with then is the integral. Okay, now 4 dx, that's 3 du, right? And the square root of 9 minus x squared, well, that's going to be the square root of 9 minus 9u squared, isn't it? And that's pretty nice because I can factor a 9 out of the bottom. So I'd have integral 3 over square root 9 times 1 minus u squared du. But that 9's coming out as a 3, so I have integral 3 over 3 square root 1 minus u squared du. So I just have the integral of 1 over square root 1 minus u squared du. Now, you know, I would keep a Google page or something handy that has integral formulas on it. And you could even do that right now. Google integral formulas. And you should find that one. The integral of 1 over the square root of 1 minus u squared. If you don't remember it from Calc 1. I don't. I have it written down here. this would be arc sine, or I usually write inverse sine. I like that notation better. Of u plus c. So that's going to be the inverse sine of, now let's see, what did we let u be? We let u be 4/3 x, right? So 4/3 x plus c. Okay, that took care of that first one. Now, how did I decide on 4/3 x? I looked at the ratio of those, of the first one and the last one, the 16 and the 9. Let's look at the integral 32x over square root 9 minus 16 x squared dx. You guys do that. Take a second and do that part. So I'm assuming you let u be 9 minus x squared, and then du would be minus 32x dx. And so what we wind up with then is the opposite of the integral of 1 over u to the 1/2 du. And let's see now, I could write that as the opposite of u to the minus 1/2 du, which would wind up being minus 2u to the positive 1/2 plus c. And then, let's see, well, u was 9 minus 16x squared. So this would be minus 2 times 9 minus 16x squared to the 1/2 plus c. Now I need to put all that together because I was supposed to integrate that whole thing from the start. So we would have the whole thing is going to be, we've got inverse sine 4/3 x. Now I got to think about that minus. I've got a minus here and a minus here. So it's going to be minus a negative, right? So the result is going to be plus 2, and I could write this as a square root if I want. 9 minus 16x squared plus c. So we kind of used two tricks there, right? We said, well, let's separate it into 2 because that minus 32x just was so nice. And then we realized that, well, when we've got that square root of a difference of two things that are squared, and they don't necessarily have to be squared because anything's a square, right? But we figured out that that ratio was going to make it nice. We could factor it out. Go ahead.
It's plus 2 root. It's plus. So how did you get the second negative to cancel?
So I am subtracting
The two intervals. Yeah.
that integral, and that integral turned out to be a negative.
And where did you get the negative? Because when you antiderive u to the negative 1/2, you add 1 to your exponent, divide by your exponent, so you divide by positive 1/2.
No, that negative was introduced here.
But then that negative came from the original integral up top.
No, that came from the derivative of that.
Oh, I see. Thank you.
It might would have been better if I would have called that plus negative 32x. Then there would have been fewer negatives to deal with. This is called integration by parts.
Have you ever integrated by parts before?
You go to the club, guy at the door,
You ever integrated
You can-
by parts?
gonna have to make you integrate by parts before you can come in. All right, so here we go. Let's think about the product rule. Now, what I've got here is a function y, and then I've got these two functions u and v. Now, I could find the derivative, couldn't I? Like I could go, well, let's see, y prime on the left, but now I've got a product rule on the right. Now let's think about this. So the product rule, that's first times derivative of second, so that would be u v prime plus the second times the derivative of the first, so plus u prime v. Okay, we could do that. Now, I could integrate it back, couldn't I? Like I could go, okay, well, the integral of y prime would be the integral of u v prime plus u prime v. And on the right, I could make that two integrals. I could make, on the left, it's just y, isn't it? So it's just y. On the right, it's integral u v prime plus integral u prime v. This is the sort of thing that you, once you see it, you go, dang, why didn't I think of that, man? Okay, so here we go. I don't, I don't know how to integrate u v prime or u prime v. Don't know how to do that. But I do know that y is uv. I do know that, don't I? Okay, so uv, that would be equal to the integral of uv prime plus the integral u prime v. Now, we've always, like when we do u substitutions and stuff, we're always looking for a function and its derivative, right? And that's always really, really handy. But I'm looking at u and v and I'm saying, well, those are two different functions. They are different functions. They're not related. Like one of them could be e to the x and the other one could be sine x. Okay, that's messed up. But here's what I know I could do. I could subtract. I could subtract this u prime v from both sides. Let's do that. So what would I have? I'd have integral u v prime would be equal to u v minus integral u prime v. Okay, we could use some other notation too. Like I could say this is integral u dv, couldn't I? And that's equal to uv minus integral, and I could call that v du. I could do that. Okay, so when does this become handy? Well, let's imagine this for a second. And this is the way I always look at this. I'm going to do a little graphic here that is the method that always works for me. Okay? I'm going to decide on a u. And then I'm going to decide on a dv. Okay? So I have two functions. I have a u and I have a dv. Now from those two then, I could figure out what du would be, because I would just find the derivative of u. And then I could find out what v would be, because I could just integrate dv. Okay, now let's look at what we have here. One, on the left side, we have u dv, right? That right there. Two, we have u times v, that right there. And c, or 3, we have v du, that right there. So this is how I always do this. I go, okay, 1, u dv, 2, uv, 3, v du. And I make that little shape for myself and it works every time. Okay, so let's look at an example of what this would be. Your life just changed. That's how you pick up chicks, isn't it, Everett? You go to the grocery store and you try to impress the cashier.
He most definitely does.
I feel like when you're from the cashier with your calculus knowledge, it's
Oh my gosh. If she could speak to me in integration terms.
All right, here we go. Integral x minus 1 sine pi x dx. What? Are you kidding me? Those functions aren't related. Okay, well, I think, though, that we have the tools to do this. All we have to do is decide on a u and a dv. Okay, so how do we pick which one? Well, you're going to do enough problems that you're going to start to see the thing, but I'm looking at it and going, well, I don't want things to get more complicated as I go through it. I want things to get simpler as I go through it. Now, if I let dv be x minus 1, and then I find the integral of that, all of a sudden I'm up to x squared, aren't I? I mean, the things get... Now, if I let u be x minus 1, then what would du be? It's just dx, isn't it? That's nice. Okay, but what about dv? So if u is going to be x minus 1, then dv is going to have to be the rest of it, right? Sine pi x dx? But it doesn't get more complicated, right, for me to integrate that. What would the integral of that be? Oh, close, except no.
1 over 5
Almost.
would be cosine over pi.
Yeah, but there's a negative. There's a negative in there too, right? Very good. So minus 1 over pi cosine pi x. That's what it would be. Right? Find the derivative of that to convince yourself. So if I have minus 1 over pi cosine pi x, and I want to find the derivative of that, well, let's see, I have a minus 1 over pi. Let's don't write that. So if this is y, then y prime would be, I'd have that constant, minus 1 over pi. I have an outside function, cosine. What's the derivative of the cosine function? Negative sign. But then I've got an inside function, pi x. Derivative of pi x is? Okay. The pi's cancel, the negatives cancel. I just have sine pi x. Okay, good. It's important, though, to check yourself. Okay, so here we go. So what are we going to do here now? Well, I'm going to do that 1, 2, 3 thing that I did. So 1, I've got this. Okay, so what I'm doing is I am integrating x minus 1 times sine pi x dx. Okay, that's good. That's there. And then that's going to be equal to, okay, now here comes the 2 part. Straight across the top. That's going to be x minus 1 minus 1 over pi cosine pi x minus, and the 3 part is to go bottom left, upper right. Integral minus 1 over pi cosine pi x dx. which I think we did. So let's go back and look. Is that what we're supposed to do? Let's look at our integration by parts. It says the integral of u dv, that's straight across, upper left to lower right, equals uv, that's straight across, minus integral v du, that's lower left, upper right. Everybody good? Everybody see the formula and the process?
Double the amount of numbers and letters on this graph. I'm excited.
All right, so here we go. Minus 1 over pi, cosine pi x, x minus 1. That might be how I write it probably. And then now we're going to have plus, right? And we just integrated that thing, didn't we? So we've got plus 1 over pi integral cosine pi x dx, integral of cosine pi x. So minus 1 over pi cosine pi x, x minus 1, plus 1 over pi. Okay, integral of cosine pi x. All right, that's going to be, let's see, integral of cosine is, yeah, positive sign, right? But I still got to deal with that pi x, right? That's going to be 1 over pi sine pi x plus some constant. Okay, now I think I can write that just a little simpler. So this is then going to be minus 1 over pi cosine pi x times x minus 1 plus, now that's going to be 1 over pi squared sine pi x plus c. There we go. Like when you got up this morning, you probably didn't think you could have done that, huh? Now you can. Any questions about any of that? Well, let's just do some more. Let's keep going. I think we need adequate practice at this. So let's see. What if we have the integral of the natural log of the square root of x dx? What? I mean, have you ever thought about how to integrate the log before? I mean, you looked at a formula, right? That's what babies do. We don't do that anymore. How else could I write this? Natural log of x to the...
To the 1/2.
Yeah.
Which is the same as 1/2 natural log.
That's true. If I have the log of something raised to a power, the power comes down front, right? What is a log? Log is the exponent, right? When you raise a power to a power, what do you do with the exponents? You multiply them, right? So this is the same as integral 1/2 natural log x dx. I can write that then as 1/2 integral natural log x dx. So, I mean, is that better? I mean, it kind of is, right? Because I don't have that square root on there anymore, so that's better. I think I need to do this thing here where I decide on a u and a dv. So I think what I'm going to do, I mean, if I find the derivative of natural log x, it gets simpler, doesn't it? It's 1 over x. Okay, so I think I'm going to do that. So u is going to be natural log x. Now, what does that leave dv to be? Well, that's just dx, right? Okay, so then du would be 1 over x dx, and v would just be x. So this is not looking difficult at all. So I've got a 1 and a 2 and a 3 here. So let's see what this would look like then. So 1, all right, integral natural log x dx equal to 2, we'll pick up the half later, equal to 2, so I've got x natural log x minus 3, lower left, upper right, integral x times 1 over x dx. That's not hard to integrate. So that's just going to be x natural log x minus integral dx, which would just be x natural log x minus x plus some constant, right? I do have a 1/2 though to deal with from the start. So I could have dealt with that all along, or we could just say, okay, then 1/2 integral natural log x dx is equal to 1/2 of all of that, x natural log x minus x plus a constant, which we could say is 1/2 x natural log x minus 1/2 x plus the constant. I wanted to do that separately, though, because I wanted you to see that that formula that you are familiar with, or you've looked up before, integral of the natural log of x, is right there. X natural log x minus x plus c. You don't have to look that up anymore. You can do it yourself. You can derive it. Matter of fact, it's going to turn out that there's several that you've looked up before in your life that you don't need to look up anymore. Yes, sir.
You don't divide the 1/2, you multiply because they're equal, then you just multiply the 1/2 as a constant at the end.
It is a constant. Yes, that's right. But why do I have a 1/2 there? Because we had a square root at the beginning. Yeah. Okay. Do some more. So let's say that we have integral z over 10 to the z dz.
Yeah, I'm converting that to x. I ain't right.
You're what?
I'm converting that to x over 10 to the x dx.
Oh, come on, man. Don't limit yourself like that.
My limit is infinity. That's not a problem.
Your job is to find your limits and go past them. Like, eat 2 bags of those things. All right.
That would literally kill me.
All right, so here we go. We need to find a u and a dv. Okay. If I let u be z, then du would just be dz. That's pretty nice. Okay, but what about 10 to the minus z dz? If I let that be dv, what's the integral of 10 to the minus z dz? Now, oh, go ahead.
10 times the natural log of the absolute values. Is that right?
Well, there's a natural log there. Do you remember, so think back to your your formulas, if you have some base that's not e raised to some power, there was a formula for that. Do you remember what that was?
ln x over ln a.
Well, yeah, it was 1 over natural log of a, and then look it up. Let's look that up, because that's going to be part of this whole thing, is making ourselves familiar with the integration formulas, because that's in the previous section too. So Google integral formulas. And I mean, like, seriously, I do not memorize these things, because you can look them up so easy. And I only have so much space in my brain.
So what you're saying is we need Google on tests.
No.
A to the x over ln
Very good. So it's just 1 over natural log a to the u plus c, right? That was the formula for integrating some base other than e. Think about it. When you integrate e to the x, what is it?
Just e to the x.
Yeah, what happened to the 1 over the natural log part?
a. It got canceled out.
Yeah, it's 1, right? It's 1 over natural log e. Natural log e is 1. Okay. All right, very good. So now we know what v is, right? So v, now let's see, that's a minus though. So I've got that to deal with. So that's going to be minus 1 over natural log 10 to the minus z. Okay, so here we go. We have our 1, 2, 3. So our integral then is going to be 1 integral z 10 to the minus z dz. Now I always write this out. And the reason is because in that very first thing over on the left, I'm checking myself. Did I write all this stuff out right? I should have this thing here, what I'm originally supposed to integrate, right there on the left. And if I didn't write it out right, then it won't be there. It'll be different. And it shouldn't be different. It should be the same. All right, so that's going to equal to, straight across the top, z times minus 1 over natural log 10, and then 10 to the minus z, minus integral. So that will be minus 1 over natural log 10, 10 to the minus z dz. Okay, so what does this turn out to be? All right. I've got, on the first term here, I'll just go ahead and call this minus z over natural log 10, 10 to the minus z. And then the next one over here, so I'm just going to go ahead and call that a plus. And I'll bring out that 1 over natural log 10. And then I've got integral 10 to the minus z dz, because I've cleaned that up, so I'm making it easier to see what the integral is going to be. But we've already integrated that. So that's going to be minus z over natural log 10, 10 to the minus z plus 1 over natural log 10. Now, we integrated 10 to the minus z dz, and we found out that it was minus 1 over natural log 10, 10 to the minus z, and then plus c. That's ugly. I think we can make that look nicer. How does it look? How would it look nicer? I mean, I guess I could get a common denominator of natural log 10 and make one term out of it, but would that really help me? Like if I needed to do something with it later, I'd probably separate it back out, wouldn't I?
I'd just enter it into Pearson like this.
Yeah, and that might work. I don't know. Does Pearson take things
Unsimplified.
particularly unsimplified sometimes?
Yeah. It depends if it asks you to like.
Yeah. Most of the time it will.
I've been getting some like really ugly looking answers because it would take like 30 minutes to simplify. Just absolute, just like, you don't even want to look at it, it's so ugly.
Yeah. Well, I guess you can consider it a matter of pride. Whatever you want to do. But, I mean, we've got one minus here. We've got a 10 to the z that could go on the bottom here. And we would actually have the square of the natural log of 10 on the bottom. I mean, that's about as simple as I think I would worry about if I was...
Where is the 10 to the z on the bottom?
It's 10 to the minus z, so it'll go to the bottom and the exponent becomes
Okay,
positive.
sorry. Yeah.
This is fun, isn't it? You have to admit it. You're enjoying yourself.
It is kind of crazy that it works though. Like you look at it and you kind of wonder why didn't I just? It just seems like a simplified version of it.
Yeah. I mean, you started, I mean, like this morning, again, when you got up, if you'd have looked at the integral of z over 10 to the z dz, you would have never imagined that you'd get down to minus z over natural log 10, 10 to the z minus 1 over 10 to the z natural log 10 squared plus c.
Makes me want to throw up. Either that or the talkies.
Yeah. All right, so here we go. Integral e to the x sine x. Ooh, I think I mentioned that one earlier. We knew we'd get there, didn't we? All right, this one's going to take a lot of strokes with the hammer. So u equals e to the x dv that leaves that to be sine x dx. Now du then would be e to the x dx. V would be minus cosine x. Okay. So, one, we have integral e to the x sine x dx, starting out well, equals 2 minus e to the x cosine x minus integral 3 e to the might as well call this plus because we got a negative e to the x cosine x dx. Okay. At this point, we would be hoping we got something easily integrable, right? That's what's happened every time before. That didn't happen this time.
Only like for that simple.
Maybe we should do it again. You want to do it again? Say yes. All right, let's do it again.
You know, that's the definition of insanity, right? Doing the same thing.
Yeah, we're proving that wrong.
Out of paper.
We're going to prove that definition wrong here. Counter examples, right?
Exceptions prove the rule, right?
So is this for the integral on the right side?
Yep, e to the x cosine x, because,
Just making
boy,
sure.
it just didn't, It didn't seem to help, did it? Okay, so here we go. We're going to do the same thing, except different. So if u this time is e to the x, then du is e to the x dx. If dv is cosine x dx, oops, I didn't mean to put a dx at the end, did I? Then v is sine x. All right, so let's keep going. So we do our 1, 2, 3 again. So 1, we have. I'm gonna do it in a different color here. We have, let's see, let's use orange. Because I'm just doing this last part here. So integral e to the x cosine x dx. Okay, so that's going to be equal to now to e to the x sine x minus integral e to the x sine x dx. What happened?
I'm noticing some matching intervals here. We finished with the same one we started with.
You say that like it's a bad thing.
I say that like it's insane. Can we simple?
What do you think? What can we do?
Okay, hear me out. We add the integral of e to the x sine x to the left side, and then we do what we just did again for both of those.
Oh, say that again?
We add e to the integral of e to the x sine x dx to the left side, and then I honestly said that because it sounded funny, but if it's actually right, then I'm just poking at it.
And that's what you should do. Very good. So, well, let's see where that takes us. And I'm just taking suggestions right now. Because this is, by the way, a trick. And I don't mean like I'm trying to trick you. I mean like this is a trick you look for. This is something you look for.
I was like, oh darn it, I fell for it.
So did that take us anywhere? Did that help us get somewhere?
Could you instead plug in e to the x sine x minus
Oh, wait.
integral e to the x sine x back into the integral of e to the sine x dx equals
You
that?
said
Like
x.
substitution, and then you add e to the x sine x to both sides, so then you get 2 times the integral of e to the x sine x. And then you can divide both sides by 2.
I'm looking at what you're saying.
Okay, so.
Yeah.
I'm looking on here to see what you're
Can
saying.
you
Say it
take
again.
the integral of e to the x cosine x, because we know what that is now.
Uh-huh.
And then plug it back into the first time we did it.
Okay, so you're saying put this here.
Yes.
Okay, let's give that a try. Okay, so we have integral e to the x cosine x dx equal to e to the x sine x. I'm sorry. I meant to make that a sine x, didn't I? Okay, and then this is going to be e to the x, and I meant to make that a cosine x. I'm looking at the wrong line. I probably should have done it in the right color. Minus e to the x cosine x, plus now we're making the rest of this e to the x sine x minus integral e to the x sine x dx. This is what you're saying, right?
And then you add the integral of e to the x sine x to both sides. So then you can do, and then you can rewrite it as 2 times the integral of e to the x sine x equals, everything else.
And the beauty of this is
Divided by 2.
Good job, Lily.
Very
That was
good.
insane. Good job, Lily.
so you got rid, the whole point that what you're after is getting rid of the integral over there on the right, right? And by doing this, you found that it looked like we were in a cycle that wasn't going to end. So, but it turns out that we just wound up with that nice multiple right there. And then there is that very nice result.
2 steps backwards. 1
Very nice, Lily. Good job. Okay, any questions about any of that? That will come up. That technique will come up. Okay, so let's see. I'm going to put one here for you guys to do. So let's do integral t square e to the t dt. Did you guys get this far? It didn't end there, did it? So it looks to me like maybe we need to do what we did last time. Start another U and V. So did you do this? And then we need to do some substituting back, right? Because we can see that this integral here is just half of that integral. Okay, so I can take this this integral t square e to the t dt. That's going to be equal to t square e to the t minus 2 times what we have here. Because that's the same as what we have above that. Everybody good? T e to the t minus e to the t plus some constant, which we can write that on the outside. So what do we have? We have t square e to the t minus 2t e to the t minus e to the t plus c. Two. Yes, thank you. You could take an e to the t out of that, couldn't you?
Wouldn't it be a plus 2 e to the t instead of negative 2?
Did I write something wrong somewhere?
You know, when you're distributing the.
Yeah, right here, right? Right there. Yeah. So plus 2 e to the t, yeah. We could take a e to the t out of that, but I don't really see how that would really help us. I mean, what's left would be quadratic. Maybe that's helpful for if something we might do with it later. But anyways. Okay, any questions there? Are you feeling pretty good about this whole integration by parts thing? Well, what if we have limits of integration? So what if we have something like integral 0 to 1 inverse tangent x dx? All right, well, let's see. I think maybe we should let u be inverse tangent x. And then that would make dv a dx, right? Now, that would make v equal to x. And what about du? What is the derivative of the inverse tangent?
1 over 1 plus u squared.
I believe that's right. 1 over 1 plus x squared? Or is it minus?
Or you can use the hyperbolic equations.
Yeah.
I got 2 plus ones.
Yeah, 1 over 1 plus x squared.
Good. dx. Okay, so let's see. Well, we're going to do an integral then, right? So we'll have 1 we'll have integral inverse tangent x dx equals 2 x inverse tangent x minus integral 3 x over 1 plus x squared dx. Okay, we're gonna integrate that x over 1 plus x squared. What are you thinking?
Separate it into 2 different, like x over. Oh, never mind.
Can't do that with the denominator, can you?
Yeah, that's right.
Yeah.
You do it again.
I mean, are you seeing something there?
Just like regular substitution.
I think so. The derivative of x squared is just 2x, right?
Oh.
So yeah, I think we don't want to make it too hard. So here we'll just go let u be 1 plus x squared. Then du is just 2x dx. So 1/2 du is x dx. So that whole part right there, that integral x over 1 plus x squared dx, that just winds up being 1/2 integral 1 over u du, right? And what is that?
1/2 times
Very good. Okay, so this whole thing then is going to be equal to x inverse tangent x minus 1/2 natural log. And because these are both going to be positive, don't really have to worry about the absolute values, plus c. But we were, this is 1 over, isn't it? Oh, no, sorry. We're good. Now, we had limits of integration, though, didn't we? So if we now think about the thing that we actually started with, we had the integral from 0 to 1 of inverse tangent x dx. Okay, we know that to be x inverse tangent x minus 1/2 natural log 1 plus x squared, and then all of that is going to be evaluated from 0 to 1. Okay, so that's going to be, starting with 1, we'll have 1 inverse tangent of 1 minus 1/2 natural log 1 plus 1 square. Then minus, and then we're going to put 0 in for the whole thing. Well, okay, well that's not going to be bad. We'll have 0 times inverse tangent of 0 minus 1/2 natural log 1 plus 0. Now, we've got 0 times 0, that's 0. And then we got 1/2 times the natural log of 1, but what's the natural log of 1? Yeah, so that whole thing is 0. So all I really have is what's in those first terms there. So let's see what that's going to become. So that's going to become, so I've got 1 times the inverse tangent of 1. Okay, so I'm thinking about the tangent function on the unit circle here. So where would the tangent be 1? You can also think about the graph of the tangent function. It has asymptotes at minus pi over 2 and pi over 2, right? And it looks like that. So we're looking for where does that tangent function have a value, a function value of 1, and what would that be? Yeah, that's pi over 4, right? Because the inverse tangent function is only defined on the right half, only where the thing is 1 to 1. So between minus pi over 2 and pi over 2. And the only place that it's equal to 1 is at pi over 4. So what do we have here then? We have 1 times pi over 4 minus 1/2 natural log, well, that's 2, right? So pi over 4 minus 1/2 natural log 2. I think that's about as simple as we can make it. Any questions?
Why'd I use an entire page on this?
Why'd you use an entire page? Because it wasn't long enough for you to flip it over and use 2 pages. Okay.
Check.
So, that's all I have for today. So, I'll look back at the other stuff. I tell you what though, don't not work on it because I didn't finish it. Work on it, and you may find that there's stuff that you do know. But we'll go back.